Going to now look at an example of calculating the height of a hydraulic jump. Remember that this analysis comes from the force approach to doing calculations in hydraulic flows. Look at the details of the lecture notes to see the derivation of all calculations, but essentially we'll get two equations, one relating the height on one side to the height on the other side of a jump, and essentially these are two solutions which give the same force due to the momentum force and the pressure force. Okay, so simple question really, and in practice all this is applying this one of these two hydraulic jump equations. So it's very straightforward. Water flows in a wide channel 10 meters cubed per meter per second, so that's flow per meter width, and a depth of 1.25 meters. Flow undergoes a hydraulic jump. Calculate Y2. So you've got Y1, the upstream depth. How high will it jump to? We've got a Q 10 meters cubed per second. Well, it could be 550. Well, the question didn't tell us that, but Q was 10. Y1 is 1.25. Velocity is just equal to Q over Y, lowercase q over Y. Froude number, well, we've got different formulas for the Froude number, but remember we've got velocity over g dm, and dm for a wide channel is just equal to the depth, similarly to a rectangular channel. So velocity is 8 meters, Froude number is equal to the velocity, which we've just calculated, divided by the square root of g, which we've got here, times the depth, y1, 2.28. So it's very fast, very supercritical, well over 1. Y2 is just an application of this equation here. Very simple. Should probably subscript that one as FR1. So Y2 is equal to Y1 over 2, times by this big bracket, square root of 1 plus 8 times FR. We did that FR squared. Close the square root, subtract 1, and close the second bracket. Alright, be careful to do that. Don't put the -1 inside the square root, and the hydraulic jump would jump from 1.25 meters to 3.46. Rather extreme example this, but illustrates simply the use of that equation. Right, we're going to look at application of force again. Force on a sluice. This is example 6, EG6 or EG5. So it's labelled wrong here. Okay, EG5, a free-flowing sluice. Free-flowing means that flows flowing out without any influence from the downstream. The opposite would be a drowned sluice, where the water is backed up and it's high up here. But it's free-flowing and there's air above, it flows below the gate and there's air above it. 2 meters wide, rectangular channel to generate an upstream depth of 3 meters. So Y1 is 3 meters. So I'm writing my depth in, and Y1 is 3 meters. B1, B2, the width is 2 meters, and Y2 is 0.5. Now 0.25. Now it would be probably slightly less than the gate opening, but we're not told any otherwise, so we'll use the gate opening. What's the flow under the gate? Well, there's not a lot of information given here, but we look at something like this, we think energy analysis, energy approach, which is what we're going to do here. Of course, there's a force on a sluice, but we first of all need to calculate the flow through this, and to do the flow through this we use the energy approach. So the energy upstream is equal to energy downstream. We're going to assume that. We need to calculate some intermediate parameters. Well, let's see, we've got a lowercase q is just the flow in the channel, which we don't know, is the unknown, sorry. And we're going to do that by calculating from our formulae that I've derived algebraically about just here, based on this energy balance equation. So you'd have to do this algebra, come up with a formula and calculate this. Now looks like something that likely to get wrong here, but because it's such a big formula, but let's have a go. So we need to go to some brackets to put the whole square root in there, or we could just do equals square root, remember to put those brackets, 2 times g times y1 minus y2 . We're going to divide all that by another set of brackets, 1 over y2 squared minus 1 over y1 squared. Close that. Need to close the square root. Q comes out to be 1.843 meters. Seems about right. Not too big. Right, let's just put some numbers in there, see if these look sensible as well. Velocity, that's velocity at 1, q divided by q divided by y1, 0.6. Okay, that's a reasonable velocity. v2 divided by y2, so it's an awful lot faster. That's very fast. Froude numbers. Remember our Froude number there, v over root g y, so velocity 1 divided by square root of g times y1. It's extremely small, so it's hardly moving. So v2 divided by square root of g times y2. So much higher, very supercritical. We'll force that. Q, we can do a couple of Q calcs, but let's try that. Q times no, not like Q. We'll do area times velocity. So y1 times b times velocity 1, 3.96. Let's just try this. Y2 times b times velocity 2. Yeah, let's get the numbers of decimals the same. Yeah, we get the same number, so that's just as a check. Oops. Right, let's calculate the energy upstream and downstream, just as another check. So equals y1 plus v1 squared divided by 2g, 3.019, and the energy is Y2 plus V2 squared divided by 2G. 3.019. Energy is the same. Fantastic. Doing things right. Now, so that's the flow into the gate, but it's a force calculation. We're concentrating on this example. Part B, horizontal force on the gate. Well, the resultant force is the opposite direction to the force on the gate, but that's what we're trying to calculate. The total force is momentum force, rate of change of momentum, and the pressure force is the force due to the change in pressure on the two sides, which is pressure at the centroid times the area for one side, minus pressure at the centroid times the area for the other side. We can write this down in some algebraically, and here is our calculation that we need to calculate. So I'm going to write total. So I've got just put 1,000 in here. I'm going to write total force, which is equal to this rho QU2 V2 minus V1, which equals rho times, we've got a Q times V2, I need some brackets in there, V2 minus V1, so 24,900 newtons. Pressure force is this expression, so equals 0.5 the half times rho times G times the width times the bracketed term, so it's Y1 squared minus Y2 squared. 87,697 newtons. So the resultant force is the pressure force minus total force, 62,777 newtons. Okay, so energy calculation combined with a force calculation. Extra example: a sluice with a rectangular channel is open such that the depth is past the gate is 0.2 meters, slightly different. If the flow in the channel is 10 meters cubed and the width is 4 meters, calculate the depth of flow upstream of the sluice. Now, okay, slightly different unknown in this one. This is the depth upstream. We know the flow this time, so we've still got an energy approach. We're still going to equate the energy upstream to the energy downstream. In fact, that's really all we've got to do any analysis of this. Let's start by applying that energy equation. Q upstream is Q is 3 meters cubed per second. The width doesn't change, it's 4 meters upstream and downstream. The depth downstream is 0.2. Q, well, we'll just lowercase q is just uppercase Q divided by the width. The velocity upstream, well, we don't know that, do we? What we do know is the velocity downstream, or we could just put in velocity upstream is an unknown. Let's just do that for now. Now, V2, let's do that, is equal to Q divided by Y. So 3.75 meters per second. Froude number downstream, let's just see what that will be. It's equal to V squared, divided by the square root of G times the depth. So this is dm is just depth for rectangular channel. Energy at 2, we'll do that, is just the depth plus V squared divided by 2 divided by G, 0.917. Now I've done my algebra previously here. I've got my energy equation written in terms of capital Q's, rearranged it, substituting a value for the depths, area for the depths, or in terms of lowercase q, and in this example it's minus y1 that we don't know. We know all this downstream side, we know that because that's the energy. Now I could put this in here. Let's edit this equation live here is equal to E2. Okay, so just that's where this equation comes from. We just rearrange this second to last equation, we get y1 cubed minus e2y2, sorry, y1 squared plus q squared over 2g is equal to 0. So the a in this equation is 1, that's normal formulation. The b is equal to minus that e2 that we just calculated there. The c is equal to 0 because we have no y1 coefficients, and d is equal to q squared divided by 2 divided by g. We can put these in our cubic solver. Let's see what the cubic solver says. It's okay, I've seem to have deleted it, so let's have a values in the function. A times y cubed plus b times y squared plus c times y plus d. Drag that down to about 35, wasn't it? We see it crosses here. Let's get a bit more focus. Change that to 0.05. Not quite. 0.06. Okay, so we can see a solution about 0.2. Let's see. Yeah, about between minus 0.2 and minus 0.14, another one at 1.6 and 0.2, and another one here between 0.82 and 0.88. Let's go back to our sheet that we're calculating here, the extension. I haven't got the calculation function in there, so it's equals can't remember what it was called, this function, so we need to go, we've included it in the with the cubic solves.function, and it's one of my user defined. So let me just go through that again. I can't remember the name of the function, but so we're in the cell, we press the F, we select user defined, and there's a few user defined here. Get highest cubic depth. There we are, A. So just click on A, click on B, click on C, click on D. I'm going to choose an X low. I remember what I did before, so 0 to 2 meters. I'm guessing I did a 30 value. It's coming up with 0.8797. We know that. So 0.88 meters for Y2. Let's just go back to our graph. Yeah, 0.88 is about where we'd expect it to be. Okay. Y crit. Do a calculation for Y crit. In fact, that's the answer. Calculate the depth of flow upstream. It's this 0.88. Let's just do some calculations to check a few of the things. Q squared. Y crit is that. The energy we're going to calculate at 2. Well, going to calculate using these two values that we would have calculated. I don't think they're necessary, but okay, let's do it completely. Let's find the 3 solutions using our cubic calculator here. So 0.87 is 1. Let's try it between 0 and 1, so it gets a -1.6, minus 0.16. Let's try this between 0.5 and 1, 0.87, 1.99. So those are our 3 solutions we get from our cubic solvers. Get used to using that. I can paste these in here as values. My E1 and E2 I can use calculating. So that E1, we'll just kind of calculate this E value equal to Y plus, well, V squared, well it's Q. Square divided by B square divided by Y squared divided by 2 divided by G. 0.9323. We'll drag that down. Oh, didn't use my formula correctly. Is correct now. So these two should be about right, but I think what I've not done is got the accuracy in that 0.19. Let me just go back and get that accuracy. Let's get the solution at 0.87. There we go. So that's the number I wanted to actually copy into my spreadsheet here, rather than just type it in. and we see that those two energy calculations are identical as a check. Okay, let me just say, why is that 2? Just show that it's not quite 2. And okay, so we've done a energy calculation to calculate the depth upstream of a sluice gate, and you can do this for many structures. Just think, this is the analysis we start with. Energy upstream is equal to energy downstream. You manipulate it to get the unknown and solve. Okay, thank you.